In this video, we're going to look at two examples or applications of systems, modeling the systems of linear equations. We've seen systems that have no solution, one solution, or infinitely many solutions. So we'll see how we can use that knowledge to help us solve these types of problems. So with any application, the first step is obviously to read the problem. And specifically when we're modeling the systems of linear equations, we want to be thinking about what are we solving for? What are the unknowns that we want to determine? So here we're told that a new airline has recently purchased a fleet of three types of planes, an Airbus A330, Boeing 767, and Boeing Dreamliner, to meet an estimated demand for 5,400 seats. The A330, those guys seat 330 passengers and cost $250 million each. 767 seats 270 passengers and costs $200 million each, while the 787s seat 240 passengers and cost $250 million each. The total cost of the fleet, which had twice as many 787s as 767s, was $4,750 million. Okay, so that's $4.75 billion. How many of each type of aircraft did the company purchase? Okay, there's our question. How many of each type of aircraft did the company purchase? Well, there are three unknowns. There's the A330, there's the 767, there's the Dreamliner. So we have three unknowns. So we can go ahead and label those. I think I'll use X1, X2, and X3. So let X1 be the number or quantity of, we'll say, I'm just going to abbreviate this, A330s purchased. We're going to let X2 be the number of 767s purchased. And we'll let X3 be the number of 787s purchased. So the question is often the thing that gives us insight into what our variables are. In fact, it explicitly says how many of each type. So that tells us what we're trying to determine is the number of each type of aircraft that gets purchased. Now, what's going to keep us from just purchasing as many as we want? What are the constraints? Well, directly, yes, the price is going to serve as a means of meeting that constraint, but ultimately the constraints are given here. The total cost of the fleet, which had twice as many 787s and 767s, so there's a constraint right there, had twice as many 787s as 767s, and then we also know that the total cost of the fleet was that amount right there. Okay, so we really have two constraints. All right, so as we go about solving this, we first of all need to convert those constraints. So I'm going to write them out. Our constraints, what is keeping us from purchasing just arbitrarily many of these, is that the total cost is $4,750 million. Now each of these are already in millions, so 4,750 will be what we insert as the total cost. We don't need to write out 4,750,000,000. This is already assumed to be in millions, as are all the costs of each of the planes. Okay, we also have that there are twice as many 787s as 767s. So there are twice as many, there are more of these. There are fewer of the 767s. There are twice as many of those 787s. Now, that's two constraints, but remember what we were trying to meet is this demand for 5,400 seats. So we need to have 5,400 seats. And we have those. We can see that those demands are being met by 270 passengers that can be carried. The 787 has 240 passengers, and I think we missed the A330. That can carry 330 passengers. So the total cost is $4,750 million. Well, for every one of these that we're going to get X1 A330s, but if we purchase just one A330, that's going to cost us $250 million. If we purchase two, if X1 is equal to 2, then it's going to cost us $500 million for the A330s. What this is hinting at is that if we take $250 million per A330 and multiply it by the number of A330s, this is in millions of dollars per A330, and this is times the number of A330s. And so that's going to cancel out and leave us with the number of millions of dollars that it's going to cost us to purchase those X1 units of A330. Similar process for the other guys. This will be 200 million per 767 multiplied by the number of those 767s, plus finally the 787 cost, which is 250 million, times how many of those there are, and we know that total cost should be 4,750. Now, yes, we are assuming we're using things up exactly. Systems of linear equations do not really give us the liberty to, find things that aren't exact. That's where we would get into what we call linear programming problems. If we had a max budget, but we didn't necessarily need to use it all up. But we know that that's how much they spent. That's what we're told. Now, for the second constraint, we're told we have twice as many 787s as 767s. So what I like to do is 787s is X3, and 767s is X2. That's how many we have. So there are twice as many 787s. So if I for example, if I had one 767, then I would have two 787s because I have twice as many. If I had, say, 15 767s, that would be 30 787s. Well, just based upon this quick little T-chart, we can see that X3 has to be twice the value of X2. So I think many people want to say twice as many 787s. So you read it literally as a sentence and literally try to convert it into symbols, and you do 2 times X3 equals X2. But it's not saying double the number of 787s to get the number of 767s. It's saying there are double the number of 787s as there are 767s. So we have to double the number of 767s to give us the number of 787s. Now finally, 5,400 seats. This is going to be a similar setup to the cost situation, but we know that every A330 can hold 330 passengers. This is passengers, I'll abbreviate that, per one A330. Well, if we multiply that by the number of A330s, then that's going to give us the total number of passengers that those A330s can collectively carry. So multiply it by X1. For the 767s, they seat 270 passengers. So plus 270 passengers times X2, the number of 767s, and plus 240 times X3 equals the number of passengers we need to seat, which is the 5,400. Okay, so we pretty much got our setup here. In the first equation, if I start creating my matrix here, x1, x2, x3 are my variables, then I'll have that followed by constants to get this set up into an augmented matrix. The coefficients of x1, x2, x3 are 250, 200, and 250. Let's just double check on that. Those are the costs in millions of dollars, 250, 200, 250. And we want that total to be 4,750 million. For the second equation, we have to be cautious because x3 and x2 are on opposite sides. So let me go ahead and subtract over 2x2, make it negative 2x2 plus x3 equals 0. You could alternatively move the x3 to the other side, and then it would be positive 2x2 minus x3 equals 0. But if you divide both sides by negative 1, you can see that those two equations are exactly identical. So it doesn't really matter which side you move things over to because the equation its meaning hasn't changed. Okay, so I have 0x1, notice this is really 0x1 minus 2x2 plus 1x3, and that's going to equal 0. And this last equation will have 330, 270, 240, and 5400. And now what we want to do is we want to perform Gaussian elimination on this to get it into reduced row echelon form from where we can read the solution. And here I've defined that matrix in a calculator. And now we'll do the reduced row echelon form. This matrix is called A. And so we get this result over here. And so now that we have that, we can see that x1 is equal to 5. Again, reading the equation off, we have x1, x2, x3, and again, our constants. And we're told that x1 is equal to 5, x2 is equal to, that's this row, 0x1 plus 1x2 plus 0x3 equals 5, and 0x1 plus 0x2 plus 1x3 equals 10. And so this is the number of each of those that we should purchase. So we should purchase they purchased 5 A330s purchased, and then we have 5 767s, and finally we have 10 787s purchased. And we could also write our solution set in our mathematical fashion by just saying that x1, x2, x3 is equal to the intersection point of these three planes at the location 5, 5, 10. All right, and we can just double check our work. We can make sure that everything works out, that our total cost is $4,750. We can double check that x3 is equal to twice x2, and you can see that 10 is 5 times 2. So we have double the number of 787s and 767s, and then you can just check that you can seat the number of passengers that's required, which is 5,400. Right, let's take a look at one more example here. Here we have traffic through downtown Urbanville, flows through the one-way system in figure 8. Okay, there's our figure 8. Traffic counting devices installed in the road, shown as boxes, count 200 cars entering town from the west each hour, 150 leaving town on the north each hour, and 50 leaving town on the south each hour. So we have just sort of this really small town, it looks like. And so there's one way in, but two ways out. So 200 people come in, 200 people leave, as we can see. So the question is, from this information, is it possible to determine how many cars drive along Allen, Baker, and Cole Street every hour? Okay, so this is hourly. This is hourly, so 200 cars entering each hour, 150 leaving each hour, and 50 leaving each hour. So as we ask this question from this information, is it possible to determine how many cars drive along Allen, Baker, and Cole Street every hour? There's our question, right? We want to know the answer to this. Now, there might be more than one answer, but we can probably imagine that given what we have, we at least know that 150 cars end up here, 50 cars end up here. So we might be able to craft more than one situation where this is true. So, for example, let's say 175 cars of these 200, 175 cars come here. Well, that must mean that 25 would come down Baker Street. And then in order to have this be true, to have 50 cars enter here, we know that the 25 cars from Baker Street can't turn into 50 cars. So, and also from Allen Street, we would expect 150 to exit over here. Well, that must mean that we lose 25 down Cole Street. And now notice that the number coming from Cole Street and Baker Street, that those sum up to 50 as they come in. So let's go ahead and define our variables. I'm going to use A, B, and C here, I think. A is the number of cars per hour along Allen Street. Okay. And then we have B as the number of cars, let's say, kind of repeat the whole thing, along Baker Street. And C is the number of cars driving along Cole Street. Okay. Now, drawing this out and seeing an example of it hopefully led us to a more intuitive understanding of what we have going on. We noticed that it must be true that, first of all, that at this fork right here, I'm going to focus on the intersections. In fact, I'm going to focus on the 3 intersections because that's where we either gain or lose cars in some cases. We know that the number of cars coming into this intersection each hour is 200. And 200 must leave, but the 200 must be split between Allen and Baker Street. So at this point, I don't think it really matters whether it's 175, 25, or maybe 160 and 40. We know that this 200, the 200 cars in, we'll just say into the intersection, equals the sum of the cars that go out. So, we have some that go down Allen Street. In fact, we have A of those. Plus we have B going into Baker Street, and this is the number of cars out. So you can think about this as you have 200 in, and that has to be the same thing as A plus B. Since if A plus B did not equal 200, well, that means that you'd be mysteriously losing cars at that intersection. So, I don't know, alien abductions or something weird like that. Now, also, what must happen here is that, notice, by the way, we didn't draw 150, but at this intersection we made it appear that 25 cars were going down Cole Street and 150 were exiting Urbanville. Well, notice that 150 plus 25 has to equal 175 because the number of cars, again, that enter this intersection has to equal the number of cars that exit that intersection. So we have not 175 cars coming in, we have A cars coming in. Remember, this right here is the value of A, and this right here was the value of B. Now, this is an interesting setup now because we have that 150 is 150 plus 25 is 175, but also if we think about it as the number of cars in must equal the number of cars out. We have A cars in. We have A cars coming in. We don't know what that number is going to be. It was 175 in our example. But then we have C cars going down Cole Street, and it must be the case that 150 are leaving Urbanville because that's what we're told. So the number of cars out will be C plus 150. And again, in our example, 175 cars per hour came into Allen Street, 25 went down Cole, and then that means the other 150 had to leave the network. So another way of thinking about this is if you take A and you subtract away C, you should get 150. And that would be true if you subtracted c to the other side on this equation as well. Now we have one more intersection to deal with. Again, the number of cars coming into that intersection, which in this case would be the 25 plus the 25, or B plus C. You have B plus C cars coming in per hour, and then you have 50 leaving that intersection, and those are the ones going into Urbanville. Now, from the appearance of things, we have these one-way streets. And that really covers our bases. So now to really answer question A, we need to get this into the correct form. So I'm going to set up an augmented matrix here with A, B, and C are 3 variables, and then our constants. So our variables in this first equation would be 1A plus 1B. We don't have any C's, so we could write plus 0C equals 200. And then here I'm going to have to subtract a C over to get 1A minus 1C. And again, this has 0 B's in this case, so that's going to be A minus C equals 150. And carry this down just a little bit here. And then we have B plus C. 1b plus 1c equals 50, which means the coefficient of a is 0. So we're ready to input this into our calculator. You can see I have the matrix put in here, and now I want to perform the reduced row echelon, or the Gaussian elimination on that matrix. So there we go, reduced row echelon form of B. Now already I see that this is not going to have a single solution. And so let's go ahead and interpret this. So after performing Gaussian elimination using technology, we get this reduced row echelon form. And we're ready to read off the equations, and we're going to do that very, very carefully just to make sure that we capture all the details. So here we're told that A minus C equals 150. Now that appears just to be this equation right here. It almost looked like there was a row that was swapped when this was performed, because this second row didn't really change at all. And that does happen sometimes. So we have A minus C equals 150. And then we have B plus C equals 50. And then we have the statement 0 equals 0, which is a valid statement. So that means it's not the case that there's no solution. But it's also not the case that there's exactly one solution, because we're not told what A and B have to be. We just are told what they have to be in relation to C. So notice that in our first row, if we look at the first non-zero pivot, which occurs in the A column, that means A is not a free variable. In the second row, our first non-zero pivot occurs in column 2, which means B is not a free variable. And we look at the third row, and there are no non-zero pivots for the variable coefficients, and therefore that does not tell us anything about the 3 variables other than C is going to be a free variable. And we can see that if you tell me what the values of C are, then A is going to be 150 plus C. B is going to be 50. It's going to be 50 minus C. 50 minus C, and C is a free variable. Okay, so we'll just say we'll choose some value for the variable called C. So we'll say C equals, I don't know, let's use a Greek symbol since A, B, and C are used up. Let's say alpha. It's going to equal alpha. That's just some number, some real number. Alpha is some real number. It could be 0, positive, negative. We don't really care at this point. And so if C is equal to alpha, then our solution set for A, B, and C, I'll write it in vector form for just visual clarity. So C is going to take on the value of alpha. We're going to assign it a number, and then B will be 50 minus that number that we assign to C. A will be 150 plus that number that we assign to C. And so from the looks of it, to answer part A, is it possible to determine how many cars drive? No, it's not, unfortunately, unless we have some additional information on the number of cars going down Cole Street. If you tell me that there are 25 cars going down Cole Street, then I know for sure that there had to have been 175 cars coming into Allen, because we know that 150 cars leave Urbanville each hour. Similarly, if you told me that Cole Street had 25 cars coming down, then that would force me to realize that Baker Street would have 25 cars coming in, since 50 cars exit that intersection. So as long as we know how many go down Cole Street, then we can determine the number of down Allen and Baker. But now what we're being asked is, what is the maximum possible traffic flow along Baker Street? How would we figure that out? Well, let's look at the solution. The maximum possible flow would be the largest possible value of B. So notice that in letter B, our variable B takes on the value 50 minus alpha. Now let's keep in mind that alpha represents the number of cars down. This is the number of cars per hour along Cole. Right? So we know that this could be as small as 0, but it could be larger from there. So if, as we get some positive number of cars per hour going down Cole, that means the number going down Baker Street are going to be smaller, because keep in mind that B plus C has to equal 50. So as Cole goes up, Baker is only going to go down. But the largest possible traffic flow along Baker Street, it can't be bigger than 50, because 50 is the number of cars exiting that intersection. So if there were, say, 60 cars down Baker Street, that would mean there would have to be negative 10 cars down Cole in order for 50 cars to exit that network. So we can take a look, we can kind of do it intuitively, but we can see that the largest max value, will be when C equals 0, and so B will equal 50 cars per hour. And I think we've kind of answered question C. What is the minimum possible traffic along Allen Street? The minimum traffic. Well, Allen Street, notice, is 150 cars per hour plus the value of alpha, the number of cars down Cole Street. Well, this 150 plus alpha, we know that alpha can't be negative, right? So we know that alpha is bigger than or equal to 0. You can't have negative cars going down. Can't have negative cars going down Cole Street. So alpha can only be at 0 or higher. Well, so that means that the smallest A could possibly be would be 150 plus the smallest value of alpha. So the min of alpha, well, I'll write it like that, is equal to 0. And the minimum possible value of that, I guess I should write the minimum possible value of C is equal to 0. And so that means that A equals 150 is the minimum number of cars per hour along Allen. What is the maximum possible traffic flow along Cole Street? Well, the maximum possible flow is the same as the maximum possible flow along Baker Street. You can't have more than 50 cars leaving that intersection. So Cole, the largest possible value it could be is 50. And another way you can see that pretty clearly is if alpha is bigger than 50, then you start getting negatives in going down Baker Street. So to answer question D, C equals 50 is the maximum value of C. And so now that we have some applications under our belt, we know that although there are infinitely many solutions and we can't have fractional cars, this actually is a situation that mathematically has infinitely many solutions. There are any number of values that you could plug in for C, which means you'll get values for B B, and A, depending on what you pick for alpha. But alpha is kind of limited between integers between 0 and 50. So even though the mathematical system has infinitely many solutions, the real-world scenario actually only has 51 possible solutions, 0 for C, 1 for C, 2 for C, all the way up to the maximum value for C, which is 50. So this system will actually have 51 practically significant solutions, but infinitely many mathematical solutions.